So we are starting another experiment. The name of this experiment is unconfined completion test of soil sample. So before starting the test, we have to know about the theory. Like unconfined completion test is widely used for a quick economical means of obtaining approximate shear strength of cohesive soil. So our target is to get the shear strength of the cohesive soil, and for that we are using some apparatus or the equipments to conduct the test. First of all, we have to take a glass plate. You can see a glass plate on which we have to prepare the soil sample, and on the glass plate you can see a mold, and there are number of parts in the mold. So whenever we are breaking the parts in each mold, we can see the different parts. There are 4 parts. The 2 parts are in the sides of the cylinder, and there is a edge part, and you can see the opening part is there. So these are the combination of mold. Now we can go for the vernier scale, slide calipers. In slide calipers there is a vernier scale where you can find the diameter of the soil sample or the cylinder, to break the cylinder we have to use screwdriver. You can see there is a screwdriver here, and for the tempering process you can see there are temping wood for the tempering purpose, and you can also see the spatula here. And now we can see the soil sample. You can see a soil sample there, and this is dry soil sample, and you can also see the beaker and the water in the beaker. And to get the dry soil sample you have to use oven. You have to use oven for the dry sample, and now we are trying to see the oven. Here you can see the oven. By using the oven we can find the dry soil sample. So let's start the experiment. So before starting the experiment, you have to combine all of the components of the mold. And you can see how can we combine the mold. And to get it tight, you have to use the screwdriver. You can see. So we are continuing the combination process of the mold. Now we have to take the soil sample and the water to get the mixing, the proper mixing. The amount of water is the 80% of the total soil sample. We are taking 200 grams of the soil sample. So the 80% of 200 grams is almost 38 grams. So we are using 38 grams of the water for the mixing purposes. You can see how the soil sample is mixed with water. So after pouring the water into the soil, we have to mix, and in that stage we should be very careful, because all of the soil components should be mixed and in a proper manner. For this purpose, we are using the spatula, which was previously shown in the experiment or the equipment for the experiment. You can see how it mixed. The soil is now getting sticky, so you have to use the spatula again and again to get the total soil sample from the glass plate. And in that step, you can see why we are using the glass plate here. So it is very easier in the workability process. So if you are using the glass plate, the workability is high rather than the wood. You can see the process, and we are almost getting closer to the process of mixing. if you are if you use the tempering process, then you can get the accurate result. Preparing the test. So we are almost filling the 2/3 of the mold, and now we are filling the last portion to get the total filling. You can see this is the last step and this is the last process to get the cylinder of the soil. However, finishing the tempering, we have to clear the surfaces or edges of the mold. So actually, in the previous pouring, to get total pouring or to get the total filling of the mold. To clean the surface. See how can we clean the surface? So we are almost finishing the stamping process or finishing the process by which we can get the cylinder of the soil. In this experiment, actually there are two steps. The first step is for the preparing purpose, and the next step is we will start to break the soil sample, and we will collecting this soil sample from this mold. Now you can see how we collect the cylinder from that mold. You can see that. First of all, we have to take the bottom portion off from the mold, and then we use the measurement of the total dimension of the hammer to get a push from the below portion, from the bottom portion. Now we are losing the mold, and this is our desired cylinder or desired soil sample, and by using this soil sample we get the strain from the machine. Okay, now we are getting closer to the compression test experiment, and after completing the soil cylinder, we have to take the height and the diameter of that mold. So we are using the slide calipers machine to take the height. We are getting that the height is 76.5 millimeter. So this is the calculation of the height, and after that we have to take the diameter of the soil cylinder. You can see the diameter is 38.6 millimeter. So we are getting that soil sample in the machine. So before starting the test, we have to describe the soil machine. Like you can see, there is a machine, and this is only dedicated for the unconfined test. And so the machine is called as the unconfined machine. You can see there are two dial gauges. The first one, which is below the machine, this actually indicates the deformation of the soil sample. So you can see if the soil sample is deformed by 1 millimeter or 2 millimeter or 3 millimeter, then this dial gauge gives us the reading of the deformation of the soil sample, and in the upper portion there is also another dial gauge, and in this dial gauge you can get the amount of the load which is imposed on the soil sample. Suppose you are giving 2 kN load or 4 kN load, then there is a reading in the dial gauge, and in that dial gauge there is a small portion where you can find the fractional values of the dial gauge. So let's start the sample taking. So we are starting the machine to get the result, to get the actual value of the load, and we are continuing this process till the breaking of the ceiling gauge. And in that case, we have to take a number of readings in different times. So we are using we are getting the reading like in this case, you take the first result, first reading. We are taking the next result, next reading. This reading is based on the completion gauge, where if it exceeds the 50 millimeter, then we have to take one reading, and next 50 millimeter we have to take another reading. So we are getting closer to the third reading. So we have to take like 50 millimeter, 100 millimeter, 150 millimeter, and this is continuing till the breaking of the soil sample. There are a number This is the almost last reading, the seventh reading, and luckily the soil absorbs the loads and the process continues. Fortunately, we can get another point. Okay, we are ending or we are getting the results. So this is the end, and we are finishing the experiment. And by calculating the axial deformation, the strain, and instantaneous area, we can find axial stresses.
This part is going to describe the calculation of unconfined compression test of soil sample. You can find the related theory, objective, materials, equipment, and the experimental procedure. In the experimental procedure, the last point is going to say to draw a compressive stress versus strain curve in the normal graph paper, and from that graph we can find or determine the compressive strength. So last of all, we have to draw a curve or graph. The beginning of the data sheet, we have to take some values like the initial diameter of the sample, that means D naught, initial height of the sample H naught, initial area A naught, which is getting by pi d square by 4, that means this is the D, so pi into d square by 4. Area is 1.79 inches square. After crushing, the height would be reduced to 75.7 millimeter, and also the diameter reduced to 39.4 millimeter. We need some calibration equation to calibrate our results. You can see the number of observations are there, and in the previous video we found there are two dial reading. One is for the load and another is calculating the deformation. So the second column describes the load providing ring dial reading in kilonewton, and the third column describing the deformation dial reading. You can see 50, 100, 150, 200, 250, 300, which was previously describing in the video. In first observation, you can find the load was 0 and all are in 0, as we are not going to give the load on our cylinder. In observation 2, you can find the load, the amount of the load is 15, that is in kilonewton, and this is denoted as x, which is used in the calibration equation. This is x. So this is 15 kilonewton. The deformation is 50 in the deformation dial reading, and the axial force, this is the load and this is axial force. Both are same, but you have to calibrate this load to the axial force in pound. So we are going to take the calibration equation like y, that means this is axial force. The result is y, 0.01 into x minus 0.002, which is in kilonewton, and if we multiply by 224.81, this would be turned to pound. So we have to take the value, that means 15, and we have to input this 15 to x, that means 0.01 into 15 minus 0.002, which is in kilonewton, and we have to multiply it by 224.81. Then we can find 33.27 in pound. Now we have to find the axial deformation, that means del L. The axial deformation would be counted by from column 3. If we are dividing column 3 by 10, we can find the axial deformation in millimeter. This is 50 and this is 5. 50 by 10, 5, 100 by 10, 10, 150 by 10, 15. And this is in millimeter. And we have to find the axial deformation in inchy, so we have to convert this millimeter to inchy. Here we have to calculate the strain. We previously knew that the equation of the strain is the axial deformation, or the deformed length divided by the actual length. The actual length would be the initial height of the sample, that means 3.18 inches. So the strain would be epsilon is equal to del L divided by H naught into 100%. The del L value would be 0.019 divided by 3.18 into 100%. You can find 0.6. Simultaneously, 0.039 divided by 3.8 into 100%. You can find 1.2. And after that, we have to find the instantaneous area. That means A. A is equal to A naught divided by 1 minus epsilon. A naught is given in the datasheet, in the beginning of the datasheet. That means initial area. That means A naught, the value of the A naught is 1.79 inches square. And the epsilon, we can find the epsilon value from this column. So we can get the instantaneous area. That means A is equal to 1.8. And the last column describes the axial stress. The axial, we know the stress means the ratio of the force and area. So we have to find where is the force. This is axial force, and this is strain, instantaneous area. So we have to divide this by this. So 33.27 divided by 1.80, that means 18.18. Column 4 and column 8. Column 4, that means 1, 2, 3, 4, and column 8 means 5, 6, 7, 8. This is 4 divided by 8. You can find the result. And after that, you have to draw a curve on the normal graph paper. In x-axis, you have to give the strain value, and in y-axis, you have to input the stress value. This is a strain, and this is a stress. Column 1, 2, 3, 4, 5, 6, 7. Column 7 and column 9. So we can get the curve like this. So from that curve, we have to take the peak value of the curve. So the peak value describe the stress, highest stress. This is QU, 84 psi. You can see this is 84 psi. And the unconfined compression test, that means the compression would be the half of QU, that means 84 by 2, this is 42, and this is the result. This is the result of the unconfined compression test. So you can see that how we get the C, or the unconfined compressive strength of the soil sample from the graph. Thank you.